In continuum mechanics, the vorticity is a pseudovector field that describes the local spinning motion of a continuum near some point, as would be seen by an observer located at that point and traveling along with the flow. Conceptually, vorticity could be determined by marking the part of continuum in a small neighborhood of the point in question, and watching their relative displacements as they move along the flow. The vorticity vector would be twice the mean angular velocity vector of those particles relative to their center of mass. Oriented according to the right-hand rule, this quantity must not be confused with the angular velocity of the particles relative to some other point. More precisely, the vorticity is a pseudovector field omega, defined as the curl of the flow velocity u vector. The definition can be expressed by the vector analysis formula, where is the del operator. The vorticity of a two-dimensional flow is always perpendicular to the plane of the flow, and therefore can be considered a scalar field. The vorticity is related to the flow's circulation along a closed path by the Stokes theorem, namely, for any infinitesimal surface element C with normal direction n and area jar. The circulation d gamma along the perimeter of C is the dot product omega, where omega is the vorticity at the center of C. Many phenomena, such as the blowing out of a candle by a puff of air, are more readily explained in terms of vorticity rather than the basic concepts of pressure and velocity. This applies, in particular, to the formation and motion of vortex rings. Examples: in a massive continuum that is rotating like a rigid body, the vorticity is twice the angular velocity vector of that rotation. This is the case, for example, of water in a tank that has been spinning for a while around its vertical axis, at a constant rate. The vorticity may be non-zero even when all particles are flowing along straight and parallel path lines, if there is shear. For example, in the laminar flow within a pipe with constant cross-section, all particles travel parallel to the axis of the pipe, but faster near that axis, and practically stationary next to the walls. The vorticity will be zero on the axis, and maximum near the walls, where the shear is largest. Conversely, a flow may have zero vorticity even though its particles travel along curved trajectories. An example is the ideal rotational vortex, where most particles rotate about some straight axis, with speed inversely proportional to their distances to that axis. A small parcel of continuum that does not straddle the axis will be rotated in one sense but sheared in the opposite sense, in such a way that their mean angular velocity about their center of mass is zero. Another way to visualize vorticity is to imagine that, instantaneously, a tiny part of the continuum becomes solid and the rest of the flow disappears. If that tiny new solid particle is rotating, rather than just moving with the flow, then there is vorticity in the flow. Mathematical definition. Mathematically, the vorticity of a three-dimensional flow is a pseudovector field, usually denoted by omega, defined as the curl or rotational of the velocity field v describing the continuum motion, in Cartesian coordinates. In words, the vorticity tells how the velocity vector changes when one moves by an infinitesimal distance in a direction perpendicular to it. In a two-dimensional flow where the velocity is independent of the z-coordinate and has no z-component, the vorticity vector is always parallel to the z-axis, and therefore can be expressed as a scalar field multiplied by a constant unit vector z. Evolution. The evolution of the vorticity field in time is described by the vorticity equation, which can be derived from the Navier-Stokes equations. In many real flows where the viscosity can be neglected, the vorticity field can be modeled well by a collection of discrete vortices, the vorticity being negligible everywhere except in small regions of space surrounding the axes of the vortices. This is clearly true in the case of 2D potential flow, in which case the flow field can be modeled as a complex-valued field on the complex plane. Vorticity is a useful tool to understand how the ideal potential flow solutions can be perturbed to model real flows. In general, the presence of viscosity causes a diffusion of vorticity away from the vortex cause into the general flow field. This flow is accounted for by the diffusion term in the vorticity transport equation. Thus, in cases of very viscous flows, the vorticity will be diffused throughout the flow field, and it is probably simpler to look at the velocity field than at the vorticity. Vortex lines and vortex tubes. A vortex line or vorticity line is a line which is everywhere tangent to the local vorticity vector. Vortex lines are defined by the relation whereas the vorticity vector are in Cartesian coordinates. A vortex tube is the surface in the continuum formed by all vortex lines passing through a given closed curve in the continuum. The strength of a vortex tube is the integral of the vorticity across a cross-section of the tube, and is the same everywhere along the tube. It is a consequence of Helmholtz's theorems that in an inviscid fluid, the strength of the vortex tube is also constant with time. Viscous effects introduce frictional losses and time dependence. In a three-dimensional flow, vorticity can be intensified when a vortex line is extended, a phenomenon known as vortex stretching. This phenomenon occurs in the formation of a bathtub vortex in outflowing water, and the build-up of a tornado by rising air currents. Helicity is vorticity in motion along a third axis in a corkscrew fashion. Vorticity meters. Rotating vane vorticity meter. A rotating vane vorticity meter was evidently invented by Russian hydraulic engineer A.R. Milovich. In 1913 he proposed a cork with 4 blades attached as a device qualitatively showing the magnitude of the vertical projection of the vorticity and demonstrated a motion picture photography of float's motion on the water surface in a model of river bend. Rotating vane vorticity meters are commonly shown in educational films on continuum mechanics. Non-rotating vorticity meters. Specific sciences. Aeronautics. In aerodynamics, the lift distribution over a finite wing may be approximated by assuming that each segment of the wing has a semi-infinite trailing vortex behind it. It is then possible to solve for the strength of the vortices using the criterion that there be no flow induced through the surface of the wing. This procedure is called the vortex panel method of computational fluid dynamics. The strengths of the vortices are then summed to find the total approximate circulation about the wing. According to the Stokes theorem, lift is the product of circulation, airspeed, and air density. Atmospheric sciences. The relative vorticity is the vorticity of the air velocity field relative to the Earth. This is often modeled as a two-dimensional flow parallel to the ground, so that the relative vorticity vector is generally perpendicular to the ground, and can then be viewed as a scalar quantity. Positive when the vector points upward, negative when it points downwards. Therefore, vorticity is positive when the wind turns counterclockwise. In the northern hemisphere, positive vorticity is called cyclonic rotation, and negative vorticity is anticyclonic rotation. The nomenclature is reversed in the southern hemisphere. The absolute vorticity is computed from the air velocity relative to an inertial frame, and therefore includes a term due to the Earth's rotation, the Coriolis parameter. The potential vorticity is absolute vorticity divided by the vertical spacing between levels of constant entropy. The absolute vorticity of an air mass will change if the air mass is stretched in the z direction, but the potential vorticity is conserved in an adiabatic flow, which predominates in the atmosphere. The potential vorticity is therefore useful as an approximate tracer of air masses over the time scale of a few days, particularly when viewed on levels of constant entropy. The barotropic vorticity equation is the simplest way for forecasting the movement of Rossby waves over a limited amount of time. In the 1950s, the first successful programs for numerical weather forecasting utilized that equation. In modern numerical weather forecasting models and general circulation models, vorticity may be one of the predicted variables, in which case the corresponding time-dependent equation is a prognostic equation. Helicity of the air motion is important in forecasting supercells and the potential for tornadic activity. Bibliography: Clancy, L.J. Aerodynamics, Pickman Publishing Limited, London, ISBN 0-273-01120-0. Weather Glossary, The Weather Channel Interactive, Inc., 2004. Vorticity. Integrated Publishing.